Vanakkam. Welcome to this course on biomedical instrumentation.
We've been looking at cardiac output and the method to measure cardiac output. And we discussed the fundamental principle of what cardiac output is in the previous video. In this video, we look at the methods of measuring cardiac output. I briefly touched upon the method in about one of the methods in the previous class. Now we will look at that in a bit more detail. So there are essentially 2-3 methods. Of course, we discuss other methods that are more invasive, which we are not interested in. We are more interested in the less invasive method, which are fixed method, dye dilution method, and the thermal dilution method. Fixed method essentially computes the oxygen consumption, the blood flow, by finding the mass rate change. dm by dt is essentially m dot. It's not. It's the amount of oxygen that is consumed divided by the pressure difference between the the oxygen difference, the amount of oxygenation in the artery and the vein. If I can know the arterial concentration of oxygen, the venous concentration of oxygen, and if I can know how much oxygen is consumed per minute, I could compute blood flow as m dot divided by Ca minus Cb. So the quantity of the substance that is observed by an organ such as oxygen in the lungs essentially is a product of blood flow to the lungs times the concentration difference of that substance between the arterial and venous blood. Why is this true? Well, actually, it's a brilliant insight. Right? If the lungs can extract, say for example, say 250 ml of oxygen per minute from blood, then let's assume that each liter of blood gives up about 50 ml of oxygen. Then how much blood will have to flow through the lungs so that you are able to get 250 ml of oxygen? Well, that is essentially the product, right? Because per each liter, for 1 liter, I'm able to extract for 1 liter of blood, I'm able to extract about 50 ml of oxygen. So that means to get 250 ml of oxygen per minute, I need to have a flow of about 5 liters per minute. Now that is, it's like, let's say you want to find out how much water is flowing through a river, for example. Okay. And what you can do is you can put 1 barrel of dye into that. If you add 1 ton of dye per minute, right, and measure at some downstream point, what the constant, by the time you assume that there is a uniform mixing and all, some point downstream, you measure the concentration of this dye. I put 1 ton. Right? Before that, there was 0 concentration of this. And after some distance, after uniform mixing, I'm having some X concentration. Means by using the concentration difference of this dye, and because I know how much dye I put in, I actually have an idea of what the flow rate is, what the flow of water is. Right? This is the brilliant insight that Adolf Fick made in 1870 or around that time, approximately that time. This is, but then what am I doing? I'm essentially assuming that the flow is a steady state, that there is no transient in your flow. No, these are all assumptions. Okay, this is actually not true. And there is uniform mixing, complete mixing between the point where you are inserting the dye and the point where you are measuring that dye. But that might not happen. Where I am measuring, there might be an increased concentration of because I cannot possibly sample all the points in the river. That is practically impossible. So you are assuming complete mixing or uniform mixing has already happened, or you are sampling, relatively accurately. And this is also not true, because truly mixing of this dye on the river requires you. But then if I sample after several 100 kilometers, you might not even find the indicator. You might not even find the dye. So there are several challenges with this. So there are assumptions that you are making. That doesn't mean that this is not an accurate method. It is. You still have to know, as a biomedical engineer, what are the limitations of the method that you use. So the approach to this method is used not just to find out cardiac output. This method is used to find nowadays, for example, how much blood is flowing to the cerebral cortex. By the way, this is a critical component for health. Is it not? Jugular vein. Through the jugular vein, how much blood is flowing? Through, for example, how much blood is flowing to the kidney, renal veins. Renal blood flow uses renal vein catheterization and other such things. So it's not a. And if, for example, I can find the difference between the oxygen in the artery minus the oxygen in the vein, the rest of the oxygen is all completely consumed. This is not actually true. This is true only for the whole body. At the level of the whole body, this is true. That doesn't mean that each organ is receiving the due share of oxygen. Note that some organs are more oxygen sensitive than others. For example, the brain is a lot more sensitive to oxygen than other organs. So individual oxygen consumption or the rate or requirement of oxygen varies between organs in the human body. This is again another topic that is beyond the scope of this course. I will request you to understand the physiology behind this, which is why you need to understand the physiology of cardiovascular function. I am not having the time to discuss this, but it turns out that some organs extract more oxygen and thus require more blood flow per unit mass of their size. For example, brain is just 2% of the 2-3% of the body's weight, but it will require 25% of the blood flow. That's an asymmetric system. There are some other parts of the body that are very big but require less blood. So it is not the size of the organ that matters, but rather how sensitive they are to oxygen, how much oxygen demanding they are. It's a complicated process. So by understanding, so this idea that arterial oxygen minus the venous oxygen essentially means this is how much the oxygen is uniformly distributed across the body is the idea that it is giving. But what is actually happening is not that. What is actually happening is that this gives the idea for the whole body, but for individual organs of the body, the oxygen demand varies. And this is something that, right? Fixed method is essentially the gold standard for finding the flow, especially in complex situations. No? And by definition, you might think that higher oxygen flow necessarily means higher, cardiac output. No, but this is not true. Higher oxygen consumption doesn't mean that higher cardiac output. You're consuming more oxygen doesn't mean that your cardiac output is this. It essentially means that the oxygen difference is higher. So despite that, so flow. So this is a combination of flow and the oxygen difference. Merely by oxygen difference, you cannot compute the cardiac output. This is the method of fixed method. This is the fixed method. So it's a brilliant insight. Do read up more about this because I'm not having the time. The other is the indicator dilution method called, or the dye dilution method. This is, you could use an indicator. For example, there are two types you could do. One is to use a color. I already mentioned you put 1 ton of a colored dye into Kaveri, and then you measure the mixed this after 1 kilometer or 10 kilometers. Well, if you measure after 500 kilometers, you will have practically find nothing. But if you measure just after 1 meter, again you might not be sampling properly. There might be a particular point at which you are going to have sufficient mixing, but not too much dilution. Well, there is a particular point at which you are going to get that. This. Okay, a similar method. You send an amount of indicator, either in this case a dye such as indocyanine green, and measure its dilution to compute the flow, which is essentially the amount of injectate times the area under the concentration curve. Well, how do you find the area under the concentration curve? That means that you need to find the concentration as a function of time, then integrate it over time. Is it not? That is the method that you are using, right? Similar discussion that so this method was formalized in the early 1900s, sometime 1920 or something like that, by Stewart and Hamilton. Essentially, the area under the concentration time curve depends only on the quantity of the indicator and not on the flow rate, not on the speed of injection or the detection of this. Essentially a function of quantity of the indicator that is used. So this is, so if you, this is because the details are beyond the scope of this course. Do check this. Okay. Then the other method is the thermal dilution method. So the cardiac output in this case, in your dye dilution method, is essentially the mass of the dye. Quantity alone matters, not the rate at which you are sending the injectate, nor the rate of flow of the fluid itself. Those are not enough. Only the mass is that matters. Remember, it is m divided by integral 0 to t c of t dt, where c is the concentration of the dye in the blood. Okay, and that I have to measure constantly over a period of time too, so that I can integrate. That is the idea. The next is the thermal dilution method. In this method, what you do is you send a particular bolus, some particular say cold saline at a particular temperature, and you know the amount of cold saline that you are introducing into the system, and you could find out, because you know the heat content of the cold saline. How do I know? Because I am the one who is sending that. I know that, and I know other things such as the density of the blood and the specific heat capacity of blood. And if I can find the change of the temperature of the blood, this is like I am having. If I am to give the example of the, if you take the river example, I am having a huge bar of ice that I am putting into the river, and then I'm measuring the temperature downstream. But there are problems, during sunny days. The ice might be melting faster because of the sun, not just because of the water with which it is mixing. It's complicated, but this is also true in blood. In the case of blood, a similar problem. It might be because there might be change in the temperature, not just because of the flow, but also because of the body temperature variations. There are other problems, but let's assume that this is the case. I could then, assuming uniform mixing of the injectate, then I will have a reasonable measure of how much of the fluid has flown based on the temperature difference. If I could compute the time, if I could compute the integral over time of the temperature difference, that means that I will have to continuously measure the temperature over a period of time so that I could integrate. If I could do that, then I could find the blood flow as indicated in this equation. Then we move on to another topic, pulse wave velocity. This is the rate at which arterial pressure wave moves through the circulatory system. It's critical to understand the physiological and physical meaning of this. Once again, please do revise your understanding of cardiovascular physiology. Note that your arteries and veins are not stiff tubes. Arteries and veins have compliance. So the shape and the geometry of the arteries and veins changes as a function of the flow itself, and the flow changes as a function of the geometry of the arteries and veins. Let me say that one more time and a little bit more slowly. The flow changes the geometry of the, say, the artery, and the artery's geometry changes the flow. Both of this happens, right? So essentially, as the pulsatile flow is happening, let's discuss only the artery case. For example, arterial pressure, where is the pressure coming from? Because there is a pump that is constantly sending out blood through the aorta, and because there is a pump, there is a high pressure at the just outside the aortic valve in the aorta, and a relatively lower pressure in a different far away artery or a capillary. Only if this pressure difference is there, only then you will have flow of blood. If there is no pressure difference, then there will be no flow. Is it not? But it is not just blood that is flowing. As this is happening, there is a variation. There is a variation in the property of the tube that the variation in the property of the blood vessel through which it flows. Right. That pressure change essentially is the pulse wave velocity. This essentially measures how fast the pressure wave travels. It is not the flow of blood that travels, but we are interested in the how fast the pressure wave itself travels through the arteries, which I could compute as this speed is that pulse wave propagation as the square root of Et divided by rho d, where E is elasticity times the thickness of the vessel divided by the diameter times the density of the vessel, which is a square root. All of this is in the square root. And critically, what this means is that the elasticity, because the thickness of the vessel is, you could assume it to be a constant, but it's not a constant because there might be deposits of fat, lipids, other such things that will change the thickness of the vessel, but also sodium that could change the thickness of the vessel. So thickness of the vessel will vary, but let's assume that that is not happening. And rho is the density of the vessel, not blood, density of the vessel, and the d is the diameter of the vessel. Thickness of the vessel, sorry, I meant the diameter can vary because of the deposits. Thickness of the vessel also is a health this. But elasticity is a different dimension, it's a different property of the material. If this compliance varies, then that will essentially affect the flow. Assume that your arteries were stiff tubes. That would make the whole process easier, right? Because if I'm just pumping and the whole blood will flow out. Why is there a need for arteries like aorta to become bigger when the blood is flowing and become smaller when the blood is not flowing? It turns out that this is what makes the aorta what it is, once again, I request you to review this material so you can understand what this is. Okay. Note that pulse wave velocity is not related to blood flow velocity. Pulse wave velocity is the rate at which the pressure wave changes through the blood vessels. Blood flow is a different concept. Pulse wave velocity is dependent on blood flow, but not only dependent on blood flow, but rather dependent on the material property of the vessel. It essentially is an indication of how much your vessel can change without becoming, how much it cannot change, for example. That is what it means. Then we are interested in the aortic valve assessment. You are interested in the computing the area of the aortic valve. Again, why this is an essential factor, why this is critical, because when the heart is contracting during systole, when will the aortic valve open? I already mentioned this. When the pressure in the left ventricle is much higher than the pressure in the aorta, then the valve will open. Note that this is a valve, which means one directional tube during which this will open. Essentially, is a critical factor to measure if there is stenosis of the aorta, or is there a constriction or a reduction in the size of the aorta. Critical factor, because this essentially determines how much systemic blood flow is going to be there. The rest of the organs, blood, heart might be pumping, but blood is not flowing. And there is some obstruction, there is some stenosis, right? So here that area is essentially Q by C times the square root of rho divided by 2 delta P, where Q is the cardiac output, C is the discharge coefficient. So coefficient times this. This essentially relates flow through the valve and the pressure gradient, change in the pressure that it creates. Critical for assessing how serious the heart the aortic stenosis is. This equation is called, what is the name of this equation? Can someone find out? Just take your time and find out what is the name of this equation. This equation was first suggested by, of course, by Richard Garland. That's why it's called as the Garland's equation. Okay, 1951. This is essentially the application of fluid mechanics and hydraulic engineering to cardiac, physiology. See how fluid mechanics can inform and inform physiology and help in biomedical engineering. Once again, check this beyond the scope of this course for me to explain this further. Okay, so with this, we come to the end of this video. In this video, we looked at three different methods: the fixed method, the dye dilution method, the thermal dilution method. Then we looked at pulse wave velocity and aortic valve area.
With this, we end this video. Thank you very much for your attention.